YouTube. In this video, we're going to explore the remainder theorem and its implications when it comes to the graph of a polynomial. But the remainder theorem, let's go ahead and read through this here. It says if a polynomial f of x is divided by x minus k. So one thing we could note here is we can use synthetic division because our divisor is of the form x minus k. Then we would say that the remainder, basically, it's where it gets its name, the remainder is equal to f of k. So the interesting thing here is this. What we're saying is that we have some f of x that we're putting into our synthetic division array. And so we have a term here, a term here, a term here, a term here, da 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 da. And what we're doing is we're dividing it by x minus k. So now here's the weird thing about it. We say x minus k. When we solve this, we get x equals k. And that's the number I would put on the outside. But according to the remainder theorem, it says that the remainder that you get when you do this is equal to f of k. So in other words, I would get something here, and then we'd put it here, and then there, and there, and there, and there, and there. But this number right here, it's really important that we make a little note here. This is equal to f of k. So long story short, what the remainder theorem is basically saying is that when we synthetically divide by x minus k, or when we plug k into the function, we get this for a y value. Or in other words, this remainder is not just the remainder, it's also the y value you get when you plug k into the function. Okay. So the remainder theorem, again, tells you that the synthetic division can be used to evaluate a polynomial function, that is, plug a number into it, because we could say to evaluate f of x when x equals k, all we'll do is this. We'll take f of x and divide it by x minus k, and the remainder has to be what that y value is, or f of k. So let's take a look at what this looks like in practice here. If I were to say, all right, use synthetic division to evaluate this when x equals -2, well, the first thing I'm going to do is I'm going to put out here -2. This is the number we want out here, this x value. And then what I'm going to do is I'm going to drop in my coefficients here. So I say 4x cubed, -2x is the second, -5x is to the first, and then 11 constants. So running through our synthetic division, we get -2 times a +4 is a -8. Adding these together, we get -10. Times a -2 here gives us a +20. 20 plus a -5 is 15. So -2 times a +15 is a -30. And then subtracting these here, we get -19. So I'm going to put a box around this. And the first thing I'm going to write is this. By the way, that is f of -2. So the profound thing about this is that if I were to make a table here, f of x table, and I were to plug in -2, then I have to get the remainder as the y value that is the output when I plug this into the function. And it also means that on my graph, when I plug in -2, I get -19. So I want you to consider before we continue here the implications of finding f of -2 using what we call direct substitution. So direct substitution would indicate that we would actually, everywhere we see an x, take it out and we would plug in this input here, which is -2. So I'll put in -2 in each of these x's here. I just want to show you this here. If we cubed a -2, we would get a -8. If we took -2 and squared it, we would get -2 times a +4. -5 times a -2 is a +10. We have +11 here. And then multiplying this out, we get -32, -8, +10, +11. So -32 and -8 is -40 plus 10 plus 11. So in other words, we get -30 plus 11, which is the same thing we got up top there, which is -19. So I'll tell you that in terms of evaluating a function, using the remainder theorem makes things a lot easier to evaluate functions that get rather long because they're polynomials. So let's take a look at these two examples here. We say given some f of x here, f of x, I want you to go find its value when we plug 5 into the function. So the way this works is that we'll put our value we're plugging in out here. We're also dividing by x minus 5 is what we're actually dividing by. But we say putting the 5 out here, we would say 4x squared, -10x to the first, -21 constants. So let's go find this y value here, which is also our remainder. So we say 4 times 5 is 20. 20 plus a -10 is a +10. And 5 times a +10 is 50. And we say 50 and a -21 is a +29. So I'm going to make a little note here. We say f of 5 is 29. So that would be our output at this input. And then our number 6 here. Let's say we want to go find what is our function value, what is our f value, when x is equal to +2. So we'll put our 2 out here that we're evaluating for. We say x equals 2 if you want to be thorough, because we are dividing by x minus 2 as our factor here. But we would say dropping in our coefficients, we have 5x's to the fourth, 2x's to the third, 0x's to the second, -20x's to the first, and we say filling in our constant here is -6. So we'll run through this a little bit more quickly here. 2 times 5 is 10, plus 2 is 12. Times 2 is 24, plus 0 is itself. Times 2 is 48. 48 plus a negative 20 is the same as 48 minus 20, so 28. And then 2 28s is 56, so adding these together here, I get a remainder of 50. But not only do I know that my remainder is 50, I also know that this is my f of 2 value. So we say when x is 2, y is 50. So that's how synthetic substitution works.